Good morning, everyone, and welcome to the CosKASI ECR seminar. It's a great pleasure for me to introduce our speaker, Daniel Muthukrishna. Daniel did his undergraduate studies at the University of Queensland, where he obtained 2 bachelor's degrees in physics and engineering. He recently completed his PhD at the Institute of Astronomy in the University of Cambridge, and is now a postdoc at Kavli Institute for Astrophysics at MIT. And today he will share his research on data-driven discovery of supernovae in the new era of time domain astronomy. Daniel, please start when you're ready.
Sure. Yeah, thanks for that, William. I'm Daniel Muthukrishna, currently a postdoc here at MIT. Thanks for the invitation to be here, and it's really great to be here. And also, I'll just briefly mention the person I know, David Parkinson. So it's really good to be at his institution now, because he was my former supervisor when I was an undergraduate at the University of Queensland in Australia. He really inspired me to pursue astronomy when I was just 19 years old or so. And I was trying to decide between engineering and astrophysics. And I think after doing a couple of research projects with him, I really changed my mind to pursue astronomy. And he was an excellent supervisor and really taught me to think like a Bayesian. And I'm very grateful to that. So I thought I'd just mention that briefly at the start. Just to an overview, what I'll talk about briefly in this talk, I lost it. All right, cool. Is most of my work I did in my PhD, where I worked on trying to build tools to detect transients in real-time surveys. So astronomy has reached this really incredible time where we have more data available to us now than ever before, and upcoming surveys such as the Vera Rubin Observatory, the LSST, are really going to transform our understanding of the transient universe. They're going to be observing millions of alerts every single night. That's orders of magnitude more than anything done previously. And I think as such, new and novel methods are really going to be necessary to process and classify this new data stream. So to that end, I've developed a few different tools. One is called Rapid, which I'll spend the first half of this talk talking about. And this does light curve classification of transient events. Another is called Dash, and this is what I worked on with David, which does spectroscopic classification. I won't talk about that during this talk, but that's a spectroscopic classification of various transient phenomena. And finally, I'll talk in the second half of this talk, I'll talk about anomaly detection and trying to do that in real time. Something that you need something separate from a classification program to do. So just to begin and to motivate this a little bit, why are transients actually important and why do we want to learn more about them? For starters, if we look at all the known elements on the periodic table, their origins all come from transient explosive events or astronomical explosive events. We've got these things called core collapse supernova, which are massive stars at the ends of their lives that explode and release massive amounts of material. And very heavy elements. We've got type 1a supernova, which are a binary system involving a white dwarf that accretes enough mass to again explode and release huge amounts of matter. And we've got kilonova as another example of something that's quite exciting right now. And this is 2 neutron stars that merge together and explode. And one of the reasons these are so exciting is that they also have a gravitational wave counterpart. So far, I've only found 1 or 2 of these events, but by combining the gravitational wave signatures with the electromagnetic signatures, we can constrain various things about gravity, general relativity, and cosmology at large. And so understanding more about these types of events really lets us understand more about the universe at large. And of course, as we all know, this is only 5% of the universe, right? The rest of the universe is invisible to us. And one of the first way we actually discovered this was again through supernova. By using supernova, or a particular type of supernova called type 1a supernova as standard candles, we were able to measure that the universe's expansion was actually accelerating. And this gave rise to the indication of dark energy, and really led to modern cosmological surveys. So that's a little bit more motivation. And then more importantly and more relevantly today, we've got this new tension where measurements of H0 between supernova the local universe and Planck in the CMB in the distant universe seem to have some sort of discrepancy and some sort of tension between them. And so this might require new physics to explain, which would be very exciting, or it might be that there are some systematics and misunderstandings of type 1a supernova. And the fact that we don't completely understand these events really does potentially lead to limitations in our measurement abilities. Then we've also got these kilonova events, which can also be used as an independent measure of H0 by using them as these standard sirens. And potentially this might be an extra plot measurement we can put on this plot that might resolve or further this tension. It's soon to be seen. But I think the fact that we don't really understand type 1a supernova is a problem. And one of the things we don't understand about it is the progenitor system and the explosion mechanism. So we still don't know whether type 1a supernova are a binary system involving a white dwarf and a massive star, where the single white dwarf accretes enough mass and reaches some change of sequence and limited explodes, or whether it's two white dwarfs orbiting each other and merging in a massive explosion. Okay, we don't understand the progenitor system, and we also don't understand the explosion mechanism, whether it is detonation or deflagration. And the only way we can resolve this is by getting observations at very, very early times and getting them early and quickly. By getting these measurements early, we can start to break this degeneracy and determine whether or not the population of supernova is from channel 1 or channel 2 or a mixture of both. And that will hopefully resolve and let us understand the population better and potentially understand whether or not there are more systematics that might resolve some of the H0 tensions I mentioned earlier. All right, so that's a bit of a motivation for why transients are important. Separately, we've also got a lot of data, right? So if we look at all the type 1a, all the supernova that we've ever observed since the year 1054, when Tycho observed his supernova in the night sky, till 2018, this is all of them plotted against the night sky, right? And we've got about nearly 13,000 supernova plotted here. And this might look like a lot, but it actually pales in comparison to what LSST is going to do, right? LSST is going to observe 10 million transient alerts every single night. That's 2 orders of magnitude more than anything done previously. And this is quite exciting and leads to a lot of new opportunities, but it's also a big problem because so far transient searches have largely relied on human eyes to identify alerts. But when you've got 10 million transient alerts a night, there's no way to automate this. There's no way to do this classification by eye, and you really do need to automate it. And the second issue is that with this much data, how do you find the needle in the haystack? A lot of astronomy has been driven by serendipity, where you get lucky, you look at the right object, and you see that there has been some anomalous event, and this allows you to look further, get spectra of it, and follow it up and find out that these things are anomalies. But when you've got 10 million transient alerts a night, again, it's very unlikely that you're going to get this lucky. And so how do you expect to get lucky with such high volumes of data? And so in the second half of this talk, I'll talk about a way that maybe we can automate this serendipity. And the other thing about the transient universe is that the more that we learn about it, the more that we learn how mysterious and unusual it really is. And so on this nice plot here, which is a parameterization of the transients we do understand in the universe, where we plot the peak brightness against the characteristic timescale of these events, we've got the whole range of supernova that we understand, transients to understand. So we've got the core collapse supernova I mentioned here and the type 1a supernova. And these gray things are basically things we understand reasonably well. And the things in the color are things that we have very, very few observations of, and we don't have complete understanding of their progenitor systems. So here we've got superluminous supernovae, these tidal disruption events. More recently, we've discovered calcium-rich gap transients and intermediate luminosity transients. We've got 1 or 2 kilonova events, and these 0.1a supernovae are still hypothetical events. And new surveys are going to discover unprecedented numbers of these objects. And we're going to need to be able to prioritize follow-up based on what type of object we think it is and on how early we think we've found it. And the other issue is that, if you look at this plot, there's these tantalizing gaps in the parameter space. And, discovery in astronomy has been driven by serendipity. So we're going to be expecting to we're going to be expecting to find things that we've never seen before. We haven't really explored this fainter parameter space at the level that LSST will do. And the shorter time scales we have barely explored, and things like the TESS or Kepler telescope are looking at this in this regime a little bit better than before. And so we need to be prepared for discovering completely new objects in real time as well, because we need to find these objects early so that we can get spectra of them while they're still live. All right, so just so we're all on the same page, what exactly is a transient? And so this is a nice picture of the dark energy camera in Chile, which is a 4-meter telescope. But just as an example, if we keep staring at the sky and take enough images, eventually something in that image will change. That change is a transient event, and in this case, it's a supernova. All right. If we take this image and subtract it from the previous image, we get a difference image. And if we look at this difference image and we plot the brightness and we count up the amount of flux in that particular area, and we plot that as a function of time, we get a light curve, and that's what we're doing here. Now you can see that the light curve evolves differently in different wavelengths of light, and you can see that by the spectrum. And if we take a filter and integrate under that, that is what we're plotting here. And if we do this in multiple filters, we'll get multiple pass bands here. And that there is, when I talk about this from now onwards, that is what a light curve is. Okay, so how do we do this? So the first thing we do is how do we actually build a classifier to determine these events? And so one of the issues is that we've got a lot of type 1a supernova, but we don't have very many of these other events. We've only observed a few of these. So I'm going to rely on a simulated training set. And so here I use the Plastic software. So Plastic is this photometric LSST astronomical time series classification challenge, which is developed by LSST Desk. And it was one of the things, it put out a challenge to the community, but more importantly, what it did is we simulated a range of different transients that mimic the properties of the LSST, which doesn't turn on until potentially next year, and mimic the observing properties such that we can simulate light curves that looked relatively similar to what we might expect to observe. I then augmented this or changed this software to, instead of doing the LSST, it matched the properties of the ZTF. And that way we can compare directly to observations. And so we simulated each of these different 12 classes, type 1a supernova, these different types of 1a supernova, type 2 supernovae, kilonova, superluminous supernovae, parent stability supernova, and so on. And I simulated about 10,000 light curves in each class, or here 4,000 light curves in each class. And this was the training set we're going to be using to try and build a classifier. Okay, and the goal here is to take these two pass bands, an R and G band, and produce a classification of what we think the class is. And what we wanted to do is we want to do this in real time. And so we developed this thing called RAPID. And RAPID, this stands for real-time automated photometric identification. And what this is able to do is, as we get new observations, so here the G and R band plotted as a function of time, our classification probabilities can evolve as well. And so here you can see at the start of this light curve, this gray line, which indicates pre-explosion, is the highest ranked class. But then as the light curve evolves and it actually starts to explode, this green line, which is a type 1a supernova, starts to grow in probability. And by the end of the light curve, we become very, very confident that this light curve is in fact a type 1a supernova. And so these classifications can evolve in time. And that was the goal we tried to do. We tried to get real-time classifications rather than classifications at just the end of the light curve. And this way you can see that, by about, a few days after the trigger being when the light curve, when the transient was first detected, we're able to confidently say that this is a type 1a supernova. So how do we build this? So we, from our training set, we use 60% of the data as a training set and use the 40% as the test set. And this is the architecture we use. So it looks very complicated and scary, but let me just break it down a little bit. So as inputs, we took multi-band photometric information. So that's the R band and G band in our cases. And so that's basically just a vector of fluxes as a function of time, these two different channels. We put a few cuts where we excluded galactic objects, corrected for Milky Way extinction, And if we knew if the redshift was input as an input, we corrected for time dilation and distance as well. And then we passed it in into a pre-processing step. And so one of the keys to our pre-processing was the way that we labeled it, right? So in any supervised classification problem, you need to have labels and data, right? So usually what you do is you label this object as just a type 1a supernova, but what we did was we labeled it as a function of time. And I said that anything before this gray dashed line, I labeled that as pre-explosion. And I taught the class to teach the classifier what the background or what pre-explosion actually looks like. And anything after this gray line, where my model thought the explosion happened, I labeled as the particular type of transient, and in this case, a type 1a supernova. We then fed this in as a big matrix into a classifier, and we did separate our data. That was our labels, and then we passed it into our deep learning algorithm. So this is our temporal convolutional neural network that we used. Okay. So before I go into exactly how this TCN works, let me just briefly talk about where these come from. And so the general idea is that you, on the bottom layer here, you pass in your light curve, for example, or sequential information. And you can do various convolutions and try to predict the next target. So before I get to exactly how these work, let me just talk about their motivation. So these sequential classifiers, or these temporal convolutional neural networks, are largely used to solve several tasks in industry. So one, for example, that you'll be familiar with is predictive text algorithms. So when you're trying to predict the next word and your iPhone is trying to predict the next word, that is typically using, or at least it was a few years ago, a temporal convolutional neural network. And more importantly, and what actually inspired the architecture for this work is how they're used on these trigger word detection algorithms. And so when you talk to your Amazon Echo or Apple Siri or Google Home device, and you say, hi, Alexa, is your device, it turns out that data looks very, very similar to a supernova going off, right? So when you say, hi, Alexa, to your device, you get nothing, 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 and then rise in magnitude and different frequencies of sound when you say, hi, Alexa. That's very, very similar to a supernova going off, right? You get nothing, 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 and then a rise in magnitude in different pass bands of light. And that similarity in the data meant that maybe we could apply a very similar approach to that's being used in these architectures that have been by industry that have invested enormous amounts of effort into making these work. Now, obviously, we've got very different noise properties and very different classes, etc. But the general idea can be quite similar. And so that's kind of what motivated this kind of architecture. And so on the bottom here, we can have our light curve, and in the output, we can have the particular class. So this is what we actually have, where it's basically a series of dilated convolutions where you take your point, a particular time series point. So in this case here, this would be the flux in the multiple pass bands at a particular point in time. And this would be the flux at the previous point, 3 days earlier, or a previous point in time, previous time step. We then pass these two into a 1D convolution. We do the same thing for the previous two outputs and the previous two again. And we pass the output of those into another 1D convolution, right? And we do this again in a dilated fashion until we can get to our output. And our output is basically a one-hot vector of the particular class. So the particular indicating whether it's a type 1a or type 2, etc. And it'll be a probability vector. And we've got this softmax layer at the end, which is basically a sigmoid function, a multi-class sigmoid function that'll put effective probabilities on our output. Okay, so this is what we did, and this worked reasonably well. And this is an example of one of the objects in our test set. We can actually extend this and look at how it performed on the other objects in our test set as well. And if we look at these classification probabilities and look at that for all 10,000 objects in our test set, we can create metrics as a function of time. And so here I plot a confusion matrix as a function of time. And so this is on the vertical axis, I'm plotting the true labels of what the actual class is. And on the x-axis, I'm plotting the predicted labels. So you can see By the end of this light curve, 92% of true type 1a supernova are predicted as type 1a supernova. And this evolves as a function of time. So you can see that these are the days since trigger on average across all the different classes, across all the different transients in our test set. You can see that as the light curves evolve, this confusion matrix gets better and better and better. And so this is, we've got a metric as a function of time showing us, that by about 20 days or so, we're doing pretty well. And here's another metric here where we plot the true positive rates against the false positive rate. So this is, we basically want a high true positive rate and a low false positive rate. So ideally, we want to maximize the area under this curve. And you can see that that's happening, that as the light curves evolve, we're getting better and better, which makes sense, right? The more data you have, the better your classifier is going to perform. And in the brackets here, I show that area under the curve. We don't perform too well at these 1bc and type 2 supernova, and that's partially explained by the poor models in the data set, which we're improving in the new version of plastic, but also partly explained by a lot of these are being misclassified as calcium-rich transients. And when we look at calcium-rich transients and compare them to type 1bc, they actually look relatively similar, so you can kind of excuse some of these results. But on the whole, it's performing reasonably well, where we've got ideally diagonals on this matrix of ones and zeros elsewhere, showing that we're performing reasonably well on the test set. And so this is our performance on simulated transients. We can then apply this and say, all right, well, how would we perform if we then apply this straight to real data? And we've had some success, right? So we applied this to real data from the ZTF, trained on these simulations, and it did reasonably well on the first pass, right? We've got, here's, for example, a tidal disruption event where just, around maximum or so, it's correctly predicted as a tidal disruption event. Here's 2 type 1a supernova. And despite having sparse data and a lot of missing data, it's still performing reasonably well. Where a few days after trigger or quite close to maximum, we're able to predict these correctly as their light curves. So we're in the process of applying this to the ZTF real-time survey through these transient brokers that exist. And we've made this software public. It's been currently applied on this Antares and LSST brokers, which are basically, these brokers are basically a way to process the amount of data that's coming from LSST and currently ZTF and release that to the community. And so they'll produce various data products, one of them being light curves, but another being classifications. And Rapid's hoping to work with them to output classifications to the community. All right, and so that's the classification half of this talk. We're able to do classifications in real time, and that's really, really great. But there's the other side of the coin, right? The other problem we've got is anomaly detection. So when we've got this much data, how do you find the needle in the haystack? Okay, so with classification algorithms, if we were to pass something completely novel that the algorithm has never seen before, it's not really clear how Rapid will adjust that and how it will react to that. And there's no way we can expect it to be able to classify an event it's never seen before. And so you really do need to have some sort of anomaly detection framework that can flag what is important and what's, what is new and novel and what's not. So a standard way to do this is, you look at your data set, you perform clustering on that data set and look for outliers, for example. You perform some sort of isolation forest, or as David mentioned before, you do some complexity method where you look at the information theory and see how complex the data is. And these are some various approaches you can apply to static data. But when you've got time series data and you're trying to do this in real time, I think it's quite a challenging problem. I don't really know the best way to solve it, but I'll talk about a couple of ways I've tried to approach this here. So just briefly, what are anomalies? We've got the known knowns, and that's what the classifier part of this work is doing. And then you've got known unknowns, things like kilonova that are relatively rare and potentially we can't trust our models for. And we've got unknown unknowns, so things that we don't know to expect. And LSST is looking at a regime that we've never looked at before, and so we'll undoubtedly find entirely new objects. When Jocelyn Bell found her pulsar event, she kind of got lucky. She was looking at the right place at the right time, and there wasn't that much data to look at. when you've got 10 million transients, you can't really expect to get lucky. And so we really need to automate what Jocelyn Bell was able to do. Can we automate and find these kinds of transients? So how do we do this? So my approach is to first build a regressive model of a transient. So that is, if we can build a model of a transient, so here I'm plotting, for example, using the data in the gray region, can I predict the rest of the light curve, so the light curve in the rest of the white region? And by comparing that prediction to the observation, that will give us some sort of, a measurement of discrepancy, and therefore some measurement of an anomaly score. So the more it deviates from the model, the more anomalous it is. So in this case here, I'm plotting the solid lines plot the median, the trace lines plot the posterior fits, and the solid line plots the median of those. But before I get to how this works, just this is the general idea, right? We want to pass in observed light curves. So observed light curves data for some supernova S at some passband P, up to some time T. All right, so that's the amount of data in the where the gray line ends. We pass in the data and the uncertainties in that data. When we pass it through some model, I've tried two models. One is a deep neural network, and the other is a Bayesian approach, a parametric approach using something called a Bayesian function, which I'll talk about in a second. And we pass it through some sort of this kind of algorithm, and on the output, we want to get the predicted flux. So the predicted flux at the next time step and the uncertainty in that prediction. By comparing our prediction to the observation, we can get some sort of measurement of anomaly score. So firstly, what is this model we're building? So the first model, given that I tried this TCN, the temporal convolutional network, for the rapid, we could probably do something very similar for this work here, where our inputs is again our light curve, but our output, instead of being the class like it was before, our output here can be the next flux in the light curve. And so then we compare that next flux, the next time step, with the observation, and we've got an anomaly score, right? Our second approach is this Bayesian model. So again, this is the architecture we've got here. And this second approach is something called the Bayesian function, which is commonly used to model transients or to model any supernova looking things. Now, this isn't really physically motivated. It is just like a parametric approach that generally can fit things that go up and then back down again. If you just tune these 5 parameters, tau fall, tau rise, T naught, the amplitude, and the offset B. If you tune those parameters, you can generally get something that looks light curve shaped. And so if we fit these to our light curves, potentially we can use that as our model. So this is our actual model where I add on some sort of intrinsic uncertainty, because we know that the Bayesian function isn't perfect, and some error in the actual data as well. Okay, and so I want to build, I'll talk about this model here. So we've already talked kind of about how model 1 works, where we take in our input as our light curve and predict the next time step. And model 2, I'll talk about that now. So we've got this Bayesian model that we want to build. And that means, we're just trying to compute the likelihood and the prior, and then measure our posterior here. So our prior is we'll take this light curve here, we'll take this model here, we'll fit it to every single light curve in our training set. And we look at the distribution of the optimal parameters, right? So the distribution of the B parameters, the T naught parameters, tau fall and tau rise, A, and the intrinsic uncertainty. By looking at these distributions, and then just we assume that the prior is Gaussian, and we'll use that Gaussian as our prior distribution. And so we know that we expect the parameters here to fall in these prior distributions. We can then define our likelihood simply as follows. We've got we assume that our uncertainties are normally distributed. And this is basically just looking at the discrepancy between our data and our model, down here. Cool. So this here, then by sampling over the multiple of the likelihood and the prior, we can get our posterior space, and that's what we've plotted here for an example light curve. So here I show the posterior fits, where you can see that, these are relatively Gaussian. We've got, we tried MC sampling first, but, that would be extraordinarily slow for the amount of data we have. So we tried some with pass approximation, which seemed to fit reasonably well. But this seems to work reasonably well. So we've plotted here our posterior fits, where the trace lines here are these posterior samples extended into an actual light curve, and the solid line is the median of those. And you can see that, as we get more and more data, our light curves evolve, and you can see that, at the start of this light curve, it underestimates the maximum, but then when it has more and more data, it is better at predicting that. So obviously our anomaly scores can improve as well. So what we can actually do is we can define our anomalies score as follows, right? So our anomaly score is defined very, very similarly to our likelihood function, but this is basically just a chi-squared, where we take our prediction, subtract it from our observation, and divide it by the sum of the variances of our predicted uncertainty and our observation uncertainty. And it's basically just the deviation between our prediction and observation summed over all the past bands. So this reduced chi-squared, we can then plot that reduced chi-squared as a function of time, And you can see that now, if we take the prediction 3 days after this gray line and plot that here, and then look at how these anomaly scores evolve as a function of time, you can see that, our anomaly scores evolve, but, the total anomaly score, the total reduced chi-squared, is close to 1, indicating the fit is reasonably good. So this is a type 1a supernova fit with a model trained on type 1a supernova. We can then compare that to how it would fit a kilonova event, for example, one of these simulated kilonova. And you can see that a model trained on type 1a supernova but fit on a kilonova produces much higher anomaly scores, as you might expect. And this is great. It's a first order success showing that, the kilonova pop out as anomalous because they are not fit well by a model trained on type 1a supernova. And that's great. So this is the first order success of our model, and we can do this, right? So we can do this not just for kilonova, but we can do it for every single kilonova in our test set and every single other transient in our test set for all the different classes. So I plot that here. So we've got our anomaly scores at the end of the light curves, and here I plot the distribution of those anomaly scores across the different classes. So you can see that most of the type 1a supernova have low anomaly scores, and they're distributed around 1. And things that look like type 1a supernova, like type 2 supernova and type 1bc supernova, also have low anomaly scores and Gaussian-rich transients, which also look similar. But things that don't look like type 1a supernova have much higher anomaly scores, right? So we've got kilonova having much higher anomaly scores. We've got intermediate luminosity transients and parent stability supernova having much, much higher anomaly scores. And if we place some sort of cut on what we define as an anomaly, say something above 3, for example, being anomalous, and things below that being being common, then we can just say that, let's follow up these objects because they're much more likely to be anomalous than these objects here. So this metric here is, this is the plot of all our distribution of points. We can actually look at what I did was I actually didn't just build it for a type 1a supernova, but I trained models on each of these 5 different classes. So I trained one on type 1a supernova, and so here on the top line here, I'm plotting the the means of these of this plot here, and I can produce one of these plots for each of these 5 different classes. And that's and so here I just plot the medians of those rather than showing all of them. And you can see that for type 1a supernova, things that are blue, things that have low anomaly scores are quite common to it. So, these type 1As, type 1BCs have low anomaly scores, but things that are in red have much higher anomaly scores, indicating that they are very different from type 1A supernova. And these are rare events, and so we should expect them to pop out as anomalous. And see that, you can see the kilonova and these microlensing events do pop out as anomalous, which is great. And you can also see that, type 2 supernova and type 1BC supernova have very similar effects, but our models for superluminous supernova and tidal disruption events aren't great. They don't really separate between the events very well. Okay, so this here was our model trained on the Bayesian function, this parametric Bayesian approach. And we did the same thing, but for the deep neural network. And you can see that the deep neural network actually has much, much poorer performance. And this is really interesting, right? It indicates that a deep neural network is really bad at finding anomalies. Like, nothing really deviates that differently from a type 1A supernova. And the reason for this is actually because deep neural networks are so good at regression and so good at predicting things, that they're so flexible that despite only being trained on a type 1a supernova, it's able to actually predict things outside its own class really, really well. So if it's able to predict things outside its class well, then it's not going to find those things as anomalous. And so we can actually look at this, and it, if we look at how the Bayesian function performs, if we, on a model trained on type 1a supernova, things that are type 1a supernova like have prediction errors that are similar, right? But things that are non-type 1a supernova like have much different prediction errors. On the other hand, the prediction errors for a deep neural network are all very, very similar. And it's because deep neural networks are so good at regression, they're so good at predicting things, that nothing really turns out to be anomalous. And so it turned out the deep neural network, this type of framework for a deep neural network, wasn't a good approach compared to a simple parametric approach, which was quite interesting. Cool. So here we've got this plot again. And what we can do is we can actually make this plot. We can actually, if we choose some threshold anomaly score, like I mentioned earlier, and then plot the true anomaly rate and false anomaly rate for those thresholds, for various different thresholds, we can create something like this receiver operating characteristic curve. And you can see here that we want high true anomaly rates and low false anomaly rates. And for things that are dissimilar to type 1a supernova, we get that, right? Things that have these seems to have very high area under the curves for things that don't look like type 1a supernova, which is great to see. And we can actually do this for every single model in our test class, in our training set. So we did this for type 1a supernova. We built this for 1BCs, type 2, superluminous super and tidal disruption events. And you can see that we have pretty good, reasonable performance for these three classes, which are all very similar to each other. And what we might say is that these classes are actually quite common, and everything else is uncommon. And so we can say, well, let's actually find transients or find anomalies with respect to these classes. So what we can do is we can take this model that we've trained on each of these, and we can sum their total chi-squareds and create an ultimate model, a combined model that combines all of these together, and we have this true anomaly rate against false anomaly rate for that. And here it's great. We can see that our anomaly scores are much higher, that the area under the curves are much higher for the classes that we expect it to be, and much lower for things like calcium-rich transients, which actually look quite similar to supernova. We can actually do this as a function of time. And you can see here that as our light curves evolve, our true anomaly rates and false anomaly rates evolve as well. And the area under this curve is evolving. And so you can see that by the end of this light curve, it's really good. Maybe by the early light curve, it's actually not that good at finding anomalies. And it does take some time to get a better prediction. And you could see earlier that we really do need to see maximum for that to be better at predicting that. If we then plot the area under this curve as a function of time, that's what we get here. And we can actually just summarize this plot by plotting the area under this curve as a function of time, and you can see that that the area under the curve does improve, and then by about 15 or 20 days past trigger, we're able to plateau out and get a reasonably good area under the curve, indicating that most things that are anomalous do come out as true anomalies, and most things that are, and the false anomaly rate is low. Okay, so I might wrap up there. And so in conclusion, we've tackled two major problems in upcoming surveys. The first is early time classification. So doing real-time classification with rapid. And we've already applied this to the real-time data stream of ZTF. And we're able to classify things in real time, which is great. And we're able to do, and the second problem we tried to solve was try to do real-time anomaly detection, which I think quite a challenging problem, but we've got an approach that works reasonably well, and I think it's a good first order attempt at this problem, I think. So I think this is a relatively new problem, and there's not much research on it yet, but it's coming along. And these two approaches together will enable us to do prioritized follow-up of new large-scale surveys based on the transient class and the likelihood of that class being anomalous. So by combining these two approaches, we can really get a sense for whether or not a new transient should be followed up or not. How likely is it to be a particular class, and how likely is it to be anomalous? And we can do early and real-time detection, which is great, and it's very, very fast. So both of our approaches are able to scale to the tens of thousands of events that will be discovered by these new surveys, and we're able to do that in just a few seconds. So that's making it scalable, and to be able to automate this in real time, being fast is really, really necessary. But yeah, I'll wrap up there, and thank you for listening.
Thank you, Daniel, for such a great talk. Is there any question from the audience? David?
Yeah, so again, thank you very much for that very nice talk. It was really good. I have a comment and then a question. So firstly, in fact, you say that you're using the chi-squared as an anomaly statistic. In the early days, if you read like statistics literature from the 1950s, they referred to the likelihood as the surprise, right? It's like how surprising is this data with respect to the model? So that was actually, so it kind of has this history, right?
Wow,
as that kind of statistic. But I think that in terms of your anomaly, you're still kind of doing classification there, right? In that how this would actually work in practice is that you would try all the models and see if they were all anomalous. In other words, like you would try this forward model and compute your anomaly statistic, and then if nothing fits, then you have something which isn't falling into any of the known classes, which is still anomalous.
Yeah.
So really, what you want is some statistic which is like averaged over all the models effectively, right? Which is some combination of all of those numbers, not just one known model against another known model, but some like diagnostic statistic which has shown that you really none of these are good fits.
Yeah.
Have you given any thought how you might do that in a kind of I like the fact, by the way, it's good to see that the Bayesian approaches outperforms the neural networks. There have to be a few applications left in cosmology where Bayesian old style Bayesian statistics is the better way to go. But if you've given any thought to how you might do this in a kind of kind of model averaged like anomaly like score or something.
Yeah, you are right. So we're looking at the deviation of a new transient to the model we've trained it on, basically. So we've trained a 1A model, and we look at the deviation for it. So the way that we've actually combined it, so I combine, in this case here, I just look at these, so I can build these 5 different models here, type 1A supernova, these 5 different models here, and I say, well, these are the common things. And I take the chi-squared we get from this approach, and I add it to the chi-squares we get from each of these approaches, and basically take the average of these 3 chi-squares and use that as my anomaly score. And so that's how I'm combining these 3 different statistics and 3 different models together. And from that, we've got these 3 separate models, and we can combine that into a single model. And I'm just basically doing that just by adding the chi-squares together. And I think that it's a reasonable attempt. It will tell you the deviation from how different it is from each of these 3 things, or the combination of these 3 things. So if it is, if it's likely, if the anomaly score for a type 1A supernova is very high but not so high for a 1BC, then those things get averaged together by the summed chi-squared.
So yeah, it's effectively like the product of the likelihoods, right? You're assuming that they're independent, and you can just take the product. But I think that there's still the question of the prior in that, right? Some of these things are just much more common, right? 1As are much more common than the other types, right? And so one option there would be to try and to do a sort of frequency weighting, right? Well, or frequency inverse weighting, where if you have something that's really rare in comparison, then you could weight it up or down in terms of the contribution to that score. But I think that works. They should work pretty well.
I think that.
Yeah, go ahead.
Sorry, go. No, you go on. Sorry.
Yeah, I think I kind of feel that there's some slightly more sophisticated sort of Bayesian approach where we could combine all of these models based on some prior like understanding of which models are more likely to be and which are slightly more, slightly rarer. But I haven't, like, I've just watched your talk now, so I haven't given any serious thought of it.
Yeah, no, I think there's probably some more thought that go in here, but I think the general idea is that if the anomaly score is high for any of these three, then for the combination of these three, then it is anomalous. And I think if we combine this with a classifier as well, and say that it produces weird results for classifiers, so it's probably not one of the classes in the classifier, but it also has high anomaly scores, then that's a little bit more telling as well. But yeah, I mean, I think that there might be something smart if you look at the Bayesian evidence or something as a potential model selection or approach, and maybe combine those as some sort of approach. But the issue with the evidence is, that's quite computationally intensive to compute often, so we want to be fast.
Well, that's cool. I understand. Thank you.
I had a quick question kind of related to what David asked. Yeah, you mentioned that this Bayesian approach performs a lot better than this neural network, deep neural network one, because DN is so flexible and too good at predicting different shapes. I was wondering if since the parametric form you introduced, this FT that goes up and down, seems quite simple in shape. Wondering if you include more parameters into this parametric form, maybe it'll be better at predicting and it'll get worse in some sense.
Yeah, no, I think that's interesting. I think there are, so this Bayesian function that I introduced is basically just creates things that look like this shape, this general shape. But that's not actually able to deal with. So some supernova have like a weird plateau point, and this functional form isn't actually able to deal with that. And so people have recently come up with more complicated functional forms that are able to take that into account. And I think it would actually be worth trying that, where you build a more complicated approach that's actually more flexible. So I mean, this is really good at fitting type 1a supernova, but maybe it's not so good at fitting some of the other common transients or relatively common transients. And so I think the nice thing about this approach is that it doesn't really matter what model you build. You can change. You don't have to build a Bayesian model. You can build another thing that fits, AGN really well if you're able to do that, because this won't fit AGN well, for example. And you can then take that ultimate chi-squared and then again do the same sum of chi-squareds as your total anomaly score. And so yeah, I think that that your model should be dependent on the particular type of class that you want to compare against. And so for this model, Bayesian is pretty good for type 1a supernova, but for type 2 supernova, I think that there are probably better models out there, that we should have probably used that instead. But the framework can actually be the same, which is nice about this approach. But yeah, I think that you might have to, you change from this simple equation here and then add on a couple of terms that'll actually allow it to deal with the plateaus and other phenomena that might happen in a light curve. I think that's probably important, yeah.
Right, thank you. Yeah, that'd be really cool to see how the difference is. It still works really well with this. Yeah. If no one's asking, I might ask another quick question about the first half of the talk about this rapid code. And yeah, sure. It was really cool how the confusion matrix changes over time as you see more and more data. And very surprisingly, like it's really good even in the very early stages. Like I thought it would be very bad. But yeah. So my question would be that it's already doing very well on type 1A, where it's like already 90% correct. I was wondering, like, can it ever get more than 90%, and can it be like 99%? What would be the main improvement for us to achieve that level of classification?
Yeah, that's a good question. So if you look here at the end of the curve, you can see that most of the misclassifications are happening for at least the type 1a supernova is happening for another type of 1a supernova called a 1ax. And 1ax is just like a peculiar 1a. It's something that we once would have called a 1a. And so you could, in many respects, say, well, let's combine these things together because it's hard to differentiate them without getting a spectrum in general. Like in general, to define a 1AX, you probably need a spectrum. And so, well, actually, if you combine all these 1As together, we actually get 97%. And so I think, you might be able to say something like that. But I think I think to actually get, to get above 92 and get 99 or whatever, I don't know. I think that's hard with just light curves, because here we've only got 2 passbands of information, and it might be that there's just not that enough information in a light curve to differentiate between all these classes. And so maybe with LSST, we've got 6 passbands of lights. Maybe that'll allow that'll be a lot more information, allow our percentages to go higher. I don't know, yet to be seen. But yeah, I mean, I think there may be other tuning things you could do, but that's what I can comment on there.
Thank you. Does anyone else have a question? Okay, I have one last more generic question, if that's okay. I thought it's really cool that you not only developed this code but also published so that other people can also work on it. And I know it'll take a lot of time and effort to make your code public, and like managing time on maintaining the code as well would be really tough. So I was wondering, just like quick advice on like main challenges you face and any tips there are to publishing code.
Yeah. I mean, I think publishing code is. I mean, I'm a big fan of open source code. I think everyone should, more of astronomy should be moving in that direction, where we just, we make everything public, and then people can scrutinize it, and it's often it's often embarrassing, because you're like, oh, what if my code isn't good enough? But most of the time, people don't actually care that much. No astronomer's code is that good anyway. And so I think you should just do it. And then once whenever I'm refereeing a paper, I always get them to put their papers out, make sure their code is public, because I think that's a good thing to do. But I think that one of the biggest challenges, it's easy enough to put your code out there, but then maintaining your code is something that is annoying, because you do end up getting a lot of emails and a lot of people trying to ask you to add on various different things to it, and that can take up a lot of time. And so I've been fortunate enough to pass this on to somebody else, the new grad student, to take over that. So I think that's probably the best approach.
but yeah. Someday I'll publish mine as well. But yeah, thank you. That it really helps like the community. Like once public, like code is public, it saves a lot of time.
Yeah, I think so. Yeah.
Right. So if there aren't any more questions, I guess we can finish the seminar.